In our second application of equilibrium, we're going to step up the chemical complexity a little bit and look at acid-base reactions. Depending on your paradigm, we can think of acid-base reactions as either the transfer of a proton from an acid to a base, or as the donation of electrons from a base to an acid. And in this series of videos, we're going to put acid-base reactions in a chemical equilibrium context and learn how to, in particular, calculate the pH of acidic and basic solutions, as well as how ions, cations and anions, can act as acids and bases respectively, and how we can understand how salts influence the pH of water when they're dissolved. Let's begin by talking about conceptual theories and models of acids and bases over the years. There are three that we'll focus on in this video, primarily dealing with the first two, the Arrhenius and Bronsted-Lowry definitions. Although the Lewis definition of acids and bases is extremely important, in particular for organic chemistry, for general chemistry we focus mostly on the Arrhenius and Bronsted-Lowry definitions. So Arrhenius's definition of acids and bases was one of the earliest. One thing he noticed experimentally was that many reagents cause an abnormal elevation in the molarity of H+ aqueous when dissolved in water. A brief comment before getting into acids about the nature of this H+ aqueous species. You'll hear me refer to this as the solvated proton, and you'll also see this written as H3O+, which is conceptually equivalent to H+ aqueous, but helps us appreciate the fact that the proton is not free on its own. It's bound in some sense to one or more water molecules. This H3O+ ion is known as the hydronium ion. So whenever you see solvated proton or hydronium, know that we're talking about either H3O+ or the equivalent species H+ aqueous. And the aqueous phase designator is very important to emphasize that this is not a free proton, it's a solvated proton. You'll hear me use these two terms interchangeably, but for the most part, I'll focus on using hydronium after this video. At any rate, Arrhenius noticed that when an acid is dissolved in pure water, it causes an elevation of the concentration of hydronium in pure water. He called these reagents acids. He also noticed that some reagents caused an abnormal elevation in the concentration of the OH- anion in water. He called these reagents bases. So when we add a base to water, that causes an elevation in the molarity of hydroxide, OH-. Hydronium and hydroxide are structurally related to water. In fact, they differ from water only by the presence or absence of one proton. And as it turns out, these species, hydronium and hydroxide, are very important for the behavior and properties of water. In a sense, what Arrhenius noticed was that acids are sort of acting like salts of H+, like H+, X-, such that when they dissolve in solution, they separate and form the solvated proton, or H3O+, if you like, and the anion that was along for the ride, X-, also in an aqueous form. This is almost like a dissolution reaction if we think of the acid as H+ and X-. Similarly, bases seem to act like salts of OH-, M+, some metal cation with OH-, such that when they're dissolved in water, they separate into aqueous M+ and the hydroxide anion. And in fact, the most famous Arrhenius bases are the salts of hydroxide, things like lithium hydroxide, sodium hydroxide, and magnesium hydroxide. We've alluded to the importance of hydronium and hydroxide in water, and one thing that's interesting about hydronium and hydroxide is that they can be generated by the reaction of two water molecules with one another via the transfer of one of the protons from one water molecule to another. Water itself has the ability, in a sense, to form the aqueous proton, or hydronium, and hydroxide at the same time through a kind of either dissociation or proton transfer process. Here's the equilibrium with the solvated proton, and an equivalent expression of this equilibrium uses two molecules of liquid water going to hydronium now, H3O+, which is aqueous, and aqueous hydroxide. These two happen to be equivalent because adding a water molecule does not affect the form of the equilibrium expression, right? Water is a pure liquid in this equilibrium, so adding an additional water molecule doesn't really affect the equilibrium. As long as we specify that H3O+ and aqueous H+ are identical, that we're talking about the same species, this is fine. For both equilibria, the Kw value is 1 times 10 to the negative 14. This is Keq, or Kc if you like, for this reaction. That means we can write the form of this equilibrium expression just by reading the balanced chemical equation as the concentration of H3O+, the molarity of H3O+, times the molarity of hydroxide. This is a very, very important equilibrium for water. In fact, in all aqueous solutions, it's always satisfied. The concentrations of hydronium and hydroxide are related in that the product of the two must always be 1.0 times 10 to the negative 14. And just as a quick reminder here, remember that H plus aqueous is not just a bare proton, and H3O plus even is not just protonated water. The true species is more like a solvated cation that we saw in the discussion of dissolution. It's more like a proton surrounded by many water molecules all coordinating to the proton to stabilize it. In any case, the important point here is that there is an equilibrium between liquid water and hydronium and hydroxide. For the most part, liquid water is H2O, but to a small degree, 1 times 10 to the negative 14 according to the K value here, water dissociates into H3O+, the hydronium ion, and hydroxide. And this equilibrium expression is always satisfied for aqueous solutions of interest. That said, the K value does depend on temperature, and that's what this graph is meant to show you. At a temperature of about 25 degrees C, we're in the usual region of 10 to the negative 14. And here the axes say 14 because we're using the P operator on Kw. And we'll talk about what the P operator means exactly in a later video. But at any rate, we're where we expect to be, around 25 degrees C. As the temperature increases, Kw actually increases to 10 to the negative 13, 10 to the negative 12, 10 to the negative 11, until it reaches a minimum right around 250 degrees C, at which point Kw starts to decrease again, back up towards 10 to the negative 12. Since Kw is equal to the product of the concentrations of hydronium and hydroxide, under normal circumstances, the two concentrations are equal, and they're both equal to 10 to the negative 7 moles per liter. This is for two reasons. In neutral water, it must be the case that the two concentrations are equal to one another, since all of the hydronium and all of the hydroxide are coming from the self-ionization of water, and the two must both be equal to 10 to the negative 7 moles per liter, so that the equilibrium expression is equal to 10 to the negative 14, the value of Kw at 25 degrees C. In terms of the Arrhenius definition of acids, then, Arrhenius acids cause an increase in the concentration of hydronium by releasing protons from their structures to the solvent, water. We can think of an Arrhenius acid as HA separating into aqueous H+, the solvated proton, or hydronium, and A-. An equivalent way to write this equilibrium involves bringing in water, and you'll often see it written this way. Aqueous HA reacts with water to form aqueous A- and H3O+. What's happened here is the transfer of a proton from HA to H2O. Since an acid causes an increase in the concentration of H3O+, what happens to the concentration of hydroxide when H+ increases? Well, since the product of the two concentrations must be equal to 10 to the negative 14, if the concentration of hydronium goes up due to the presence of an acid in solution, the concentration of hydroxide must go down. The two are inversely proportional to one another. Arrhenius bases have the opposite effect. They cause an increase in the concentration of hydroxide by simply releasing hydroxide into solution. Arrhenius bases are salts of the hydroxide anion, as we mentioned before. A good example of an Arrhenius base equilibrium involves the solvation of NaOH. In aqueous solution, NaOH splits apart into Na plus and OH minus, and it's the addition of OH minus to the solution that makes NaOH a base. Let's think again about what happens to the concentration of hydronium when the hydroxide concentration increases. Once again, when we add a base to water, it still must be true that the product of the concentrations of hydronium and hydroxide must be equal to 10 to the negative 14. This is just a condition of being in equilibrium in an aqueous solution. That means that if the concentration of hydroxide goes up due to the presence of a base, the concentration of H3O+ must go down proportionally. The Arrhenius definition was useful for understanding effects on hydronium and hydroxide concentration of acids and bases, but Bronsted and Lowry took this definition a step further and said there's nothing really special about water, hydronium, and hydroxide. A more general theory of acids and bases recognizes that acids donate protons while bases accept protons. Under this more general paradigm, we can actually only follow protons as they get moved from acids to bases. In general, then, an acid is still something that gives up a proton in aqueous solution. But we think of this proton as donated to the solvent. When the solvent is water, this is simply an aqueous proton. A base accepts a proton, and we think of a base as accepting a proton from water. Notice that H2O becomes hydroxide and it's lost a proton, and that proton has found its way into the base to form Hb+. The positive sign comes from the fact that we're transferring a proton, a positive particle, from H2O to the base. As a result, there's a negative charge left behind on hydroxide. The proton accepted from the solvent is the one that we find within Hb+. Notice in particular about this picture of bases that it expands our concept of what a base can be. Salts like sodium hydroxide and lithium hydroxide are still considered Bronsted bases because they can still, for example, grab a proton from water to form H2O and hydroxide. But the Bronsted-Lowry paradigm brings in other species that can grab a proton from water using, for example, a lone pair within their structure to form hydroxide from a water molecule. This process is called deprotonation, and it's the mechanism by which a Bronsted base elevates the concentration of hydroxide in solution. Species that differ by only one proton in the Bronsted-Lowry paradigm can be interconverted by a Bronsted-Lowry acid-base process. So for example, we can convert HA into A- simply by dissociating a proton from it. These pairs, which are related by one proton, are called conjugate pairs. In this equilibrium, HA is called the conjugate acid since it contains one additional proton. It contains an extra proton, while A- is called the conjugate base since it's missing that extra proton. We can play the same game for a base association equilibrium where a base is grabbing a proton from water. When the base has gained a proton, this is the conjugate acid form since it has an extra proton within it. This is the conjugate base form on the left-hand side since it's missing that extra proton. In the language of the Bronsted-Lowry paradigm, a conjugate acid donates a proton to the solvent to transform into its conjugate base, and a conjugate base accepts a proton from the solvent to transform into its conjugate acid. Identifying conjugate acids and bases is going to be an important skill when working with the Bronsted-Lowry paradigm. So let's practice this skill on the species we see here. To generate the conjugate acid, we simply add a proton to the structure. That's going to involve going from NH3 to NH4, for example, and increasing the charge of the species by 1, since a proton is a positively charged particle. We can play the same game with H2S. To generate the conjugate acid, we add one additional proton, and we increase the formal charge of the species by 1 unit, since a positive particle has been gained in going from a species to its conjugate acid. For ethanol, we do the same thing, noting in this particular case that the additional proton will be added to the oxygen atom, which is the only atom in this structure that contains lone pairs, the only atom that can act as a base and grab a proton. We're going to add an additional hydrogen to the oxygen and make the formal charge of the oxygen positive to generate the conjugate acid. To generate the conjugate base, we remove a proton from the structure. In NH3, we simply go from NH3 to NH2, and since we removed a positively charged particle, the formal charge of the species goes down by 1. Same idea with H2S. We lose a proton from the structure, and the formal charge goes down by 1, making this negative, and you'll notice that this is kind of a sulfur analog of hydroxide, if you like, HS-. For ethanol, we remove a proton, and in particular, for reasons that I won't get into, we want to remove this most acidic proton on the far right to generate CH3, CH2O, and now the formal charge, since we removed a proton, will go down by 1 on the oxygen atom, and we'll have a negative charge there. So to generate the conjugate acid, all we did was add 1 proton, and to generate the conjugate base, all we did was remove 1 proton. Very briefly, the Lewis paradigm of acids and bases shifts the focus from the proton, a positively charged particle, to the electron, the negatively charged particle, which is grabbing the proton. Lewis's idea was that chemical reactions amount to the reorganization of electrons in molecules. We can think of electrons being driven, for example, by Coulombic attraction or repulsion. So if we really want to understand reactions on a deep level, we need to appreciate how electrons flow from regions of high negative charge to regions of high positive charge. This is essentially the Lewis acid-base paradigm. A Lewis base is something that serves as an electron pair donor, the purple structure in this figure, while a Lewis acid is something that can accept an electron pair, a region of relatively high positive charge, like the blue structure you see on this figure. When this happens, the resulting equilibration may be thermodynamically favorable, and this is part of what drives chemical reactions to go forward. And this is how Lewis understood acid-base reactions, that the base was donating a pair of electrons to the acid, which could be a proton like H+, or could be anything with partial or full positive charge. For example, ammonia has a lone pair that it can donate to boron in BH3, which is a Lewis acid because of its incomplete octet and its lack of electrons.